And so the basic structure is represented here. So these are cobalt oxygen 2 slabs. So actually you have a triangular array of cobalt in these slabs. And then each cobalt is at the center of an oxygen octahedral. And these oxygen octahedra are tilted compared to what you would have in a perovskite structure, for example. So it's a phase sharing configuration. And then you can put various structures in between these slabs. So for example here a sodium layer. And usually these structures can donate electrons to this plane. So that's a way to tune the number of electrons you have in the cobalt oxygen to these slabs. So these materials are actually known for quite some time. So for example, if you put lithium here instead of sodium, you get pretty good batteries, and that's maybe what you've got in your cell phones. But in our community, there was somehow we discovered a few years ago when a Japanese group reported superconductivity in one of these phases. So it's quite a curious phase because to get superconductivity, you have to put water instead of sodium in between the plane. And if you don't have water, or if the sodium concentration is very different from that, you just don't get superconductivity. So you see that in this case, superconductivity appears at about 4 Kelvin. So it's quite a low temperature, and it has not been found with higher temperature since then. But then there was some sign of unconventional superconductivity, and cobalt is a 3D element like copper. So these metals, to some extent, they can be described as doped multi-insulators. So this discovery has raised some interest and some questions about whether they should be similar to filtrate or not, and so on. So about the same time, another interesting property of these materials was highlighted is that these materials have a high thermoelectric power. And that's something that is quite unusual because they are quite good metals, and usually you don't have high thermoelectric powers in good metals. So it's basically because to get high thermoelectric power, you need to have a lot of entropy, so a lot of different ways to distribute your electrons in the lattice. And that's typically not what you get in a metal where all sides are more or less equivalent. So on the other hand, for the applications, it seems that it's important to, what they are looking for is precisely to build, for example, some efficient thermoelectric device or things like that. They need at the same time a high conductivity and high thermoelectric power. So this type of materials are very good candidates for that, and they are some of the best in this category. So what was measured here is that this thermoelectric power has a strong dependence as a function of the magnetic field, and this is also something unusual, and it suggested that maybe the spin entropy is an important contribution to the thermoelectric power in this case, and so this could be also a new way to get high thermoelectric power and things like that. Okay. That was interesting in this case. So after that, people have started to study this class of materials much more systematically. So in the first part of this talk, I will try to review a little bit the different properties that you can find as a function of doping. So indeed, you can find many different properties. So you have superconductivity, but also magnetism in some other phases, very strange type of charge orderings, this high thermoelectric power. So all of this as a function of the number of electrons you put in the plane. So basically, here you have a T2G band where you can put 5 to 6 electrons, so it's a narrow band. You expect some correlation near these integer fillings. And I think what is surprising in these materials is that if you look at the different properties as a function of this band filling, it seems that the correlation are increasing when you get to the point where the band is almost completely filled. So that's something that is a little bit counterintuitive, and that's really the thing I will try to discuss. Why do you have a correlation in this limit, how they are changing with doping and so on. So to discuss that, I will mainly use ARPES experiments. So it's basically because it's what I'm doing, but you can also have a nice piece of information with ARPES about this problem. So one thing you can do, for example, is to look at the 3 different bands that are supposed to form these T2G bands to see what are the bands that are present at the Fermi level, how many electrons it contains, and all of that, to try to understand the role of the different bands in the properties of this material. So maybe you've heard about the problem of the missing Branchi pockets in these cobaltates. That's something that has been quite much debated, and I will discuss that also. And then the other reason why ARPES is very interesting is because it's a very sensitive form of the nature of correlation. So we show that indeed the ARPES line shape gives you quite direct answers about the strength of correlations in this matter. That seems also to indicate high correlations in this kind of phase diagram together with other probes who have also shown this high correlation effect. So of course, since then, we would like to understand this to answer this question: where do this electronic correlation comes from? So you see that question marks start to appear in this part. So I don't think we know at this point how to describe correlation in these phases. But I will discuss two directions which I think are interesting. Gives interesting ways to reintroduce correlation in this limit. So the first idea is one that was discussed mainly by the group of Cagliari, and it's basically it's to create new objects by coupling many different degrees of freedom that you have in systems like spin, orbital, and charge. So this creates this will be the new excitation of the systems, and they are typically much more heavier than regular electrons, and that's can explain that they behave quite differently. So another direction that is also interesting is to start from these charge orderings that are known to be present in this limit in these compounds, and to see if this could explain that you have a highly correlated state here. Okay, so I'm showing you here the structure again. So here you see the cobalt oxygen 2 slabs from the top. That's cobalt atom in blue. And so now, depending on the number of sodium, you will change the number of electrons in this plane. So if you had absolutely nothing in between the plane, so you would have only cobalt oxygen 2, and all cobalt would be cobalt 4 plus, which corresponds to 5 electrons in this 3D band. So unfortunately, this compound is not really stable because you need something to bound the different the two planes. But that's what you would get. And then if you increase the number of sodium, you would progressively get up to one more electron per cobalt 3 plus for every side, and 6 electrons in the 3D band. So the 3D bands are represented here. So they've already been shown quite some times. So you know that you have this T2G and EG bands in this octahedral environment for cobalt, and that the T2G bands will be stabilized because they don't point directly to the oxygen, so it's more favorable from electrostatic point of view. So we are going to put 5 to 6 electrons in this T2G space. And so in this case, the oxygens are tilted. So this gives a particular ball to this direction that is perpendicular to the cobalt oxygen 2 slabs. And indeed, you usually have some trigonal distortion, so which means that this octahedral is a little bit squashed in this direction perpendicular to the plane. And so this distortion will lift the degeneracy between the T2G orbital. So you will do a linear combination of these 3 T2G orbitals to get one orbital that is pointing perpendicular to the plane. That's this A1G orbital here. And then you have the 2 other orbitals which with E1G symmetry. So one important question, of course, is what is the degeneracy, the crystal field splitting between this A1G and E5G orbitals? And so that's something quite difficult to compute because it depends on many different things. I will return to this point a little bit later. So it's not only the ionic configuration that is giving you the value of delta, but also the ways the orbital hybridized, and not only these 2 TG orbitals with the oxygen, but also the EG orbitals and so on. So that's things that are discussed in this paper, for example. And of course, depending on this value of delta, you could have quite different limits. If it's very large, then you can completely forget about this orbital degree of freedom. You have basically a high-field band, the situation that is very simple, and that will be also very similar to the Brouet, for example. You could expect this state to be somewhat insulated. Now, if you really have to take into account the 3 bands at the same time, so you have multi-degenerate multi-band systems, really, and as has been discussed many times, you know that it's this will change a little bit. For example, the U over T ratio, where you can expect this much insulated transition, so it's a little bit different. Okay, so now in the solid, we will have dispersion of these states. So this is a band structure that was calculated by LDR by David Singh, for example, in 2000. And so probably the first thing to notice here is that this is a very narrow band, so just 1 eV. And this is really due to this phase shearing configuration of the octahedral, where the overlap between two cobalt neighboring sites is not very favorable. It's not as strong as what you would have, for example, in a perovskite structure, where you have copper, oxygen copper bond that is very strong with EG orbitals and so on. This gives you a larger band, like 4 eV. So here, the overlap is not as strong, and you start with a narrow band where you would expect correlation effect. So another thing that we are interested in this calculation is to see what is the composition of orbitals you will find near the Fermi level. So you see that mainly you find this orbital here in red, which has the A1G symmetry. So the A1G character is indicated as the size of the markers here. And these crossings are giving you this sheet of Fermi surface, this hexagonal sheet of Fermi surface. Then you also see that this A1G band is overlapping very strongly with this E'G band, and that one of the E'G should even cross the Fermi level in this calculation and give you these small pockets of E'' symmetry near the different K bonds. So, of course, there are not many electrons in this pocket, but they give you quite a high density of states because this band here is very flat. And so, for many properties of this material, it's quite important to know if these E'' pockets are there at the Fermi level or not. Okay, so now we're going to change the number of electrons in this phase. So this was calculated for 0.5. If you change the Fermi level, you see in fact different properties. So this was an early investigation of the different properties as function of X done by the group of Bob Cava. And what you can see here on the resistivity is that most of these phases are metals, except this one here, which is at 0.5, where you have a metal insulator transition at 50K, and which is probably due to the special ordering of the sodium that you find in this phase. But otherwise, you've got metals. But one thing that is very striking is that this metal, if you look at the magnetic susceptibility, they seem to behave quite differently if you are in this part of the phase diagram or in this part. So in this part, if you look at this blue point here, so that's also the part where you find superconductivity, you've got a temperature-independent almost susceptibility, so that's really what you would expect for the possible susceptibility for a metal. And then when X is increasing, you've got more and more temperature dependence, and it looks like a Curie-Weiss susceptibility. So of course that's not what you would expect for a simple metal, but we know that if we have a correlating metal, we can have maybe stronger magnetic correlation that will give you this type of temperature dependence. But so what is surprising here is that you would really understand that you have this strong magnetic correlation where you are near these states here, where all cobalt sites have spin 1/2, and so you're very near these states, which could be a Mott insulator, and where you could expect that you have strong magnetic correlation on this triangle lattice that is frustrated and so on. But in this part of the phase diagram, you see no evidence for these spin correlations, and it's really when you go up to here, where you don't have so many spin 1/2 left, and where you don't have, well, correlation should be should have strongly decreased because you're quite far from this Mott insulator, that you seems to have this sign of magnetic correlation. And it's also there that you find some spin density wave ground states that are telling you that you've got some magnetism in this phase.
Question. I see sort of me there on the right part of the susceptibility plot. Does it mean that at high temperature regime, even in the left part there, it somehow goes to Curie-Weiss behavior?
You mean, do you see this temperature dependent instead?
No, I see there is sort of angle on those to the right, further to the right, to the right, to the right. Yes. After that, is it Curie-Weiss behavior?
Actually, yes. I will. So I will just return to that, yes, in just a moment. Okay. So here, the main thing we can say, it seems to be counterintuitive because you would expect a little bit the opposite behavior. So what we know about this correlation, and this will be a part of the answer to your question, is that so in this spin density wave ground states, so you have ferromagnetic ordering in planes. This was measured by neutron antiferromagnetic from plane to plane. And with NMR, I don't have time to detail that, but you get also some information about the nature of the correlation in the metallic space. And it has been shown that there are ferromagnetic correlation in this space and antiferromagnetic correlation in this space. So in fact, you have two different types of metals. You should look at them with different types of correlation. And with some kind of boundary here with terms around 0.6. And so if you look at these papers, they discuss a little bit what you were suggesting, that maybe you have this QAVICE temperature which is just shifting with X and which will be at a much higher temperature. This is actually the maximum of the susceptibilities that you can measure. So I don't think that they measure up to very high temperature to really know if it's decreasing again or not. But so then, now I will focus on this part of the phase diagram where you have all these anomalies of spin and separate concentrate, strong ferromagnetic correlations with this QAVICE susceptibility, and also high thermometric power. And in fact, it seems that this boundary between the two states corresponds to some enhancement of the correlation. So there is a very nice work by a group of backlog with specific heat measurements, which have extracted the effective mass as a function of X. And if you just look here at the red points, you see that precisely at this limit of 0.6, it seems that the effective mass is increasing. Okay. So another thing that is very strange in this part of the phase diagram is something that has been revealed by NMR. So mostly the group of Henri Alloun. So if you have questions about that, I'm sure you will be very happy to discuss some of the details with you. But what is very clear from NMR is that you have two different types of cobaltates. And so one of these cobaltates, where you have here this very narrow line, which is typical of non-magnetic cobalt 3+. And the other cobaltates have very different properties and corresponds to the metallic size. And in some cases, it has been possible, so at this composition of 0.67, to map the distribution of these cobaltates, how they are ordered together. And it was found that these metallic cobaltates form a Kagome lattice here, and at the center of each of these Kagome crosses, you find a cobalt 3+ state. So it's so in this case, so this cobalt 3+ state corresponds to the cobalt we see sodium that is just above or below them. So it's believed that this sodium plus ion can stabilize this electron on some of these cobalt sites that are thinking directly beneath them. But then here you have, of course, quite different metals than the regular triangular cobalt plane that you would expect. And of course, you can ask whether how will it change the electronic properties of the metallic state? Could it lead to new correlation effects?
Excuse me, the yellow and the brown, just if it's up or down, or is it there's some difference?
No, they are a little bit different, but basically they are all cobalt sweepers, and I refer you to Aaron for all details. Okay, so in fact there are two different families of cobaltates where you can find this high doping range. So I've been discussing so far these sodium cobaltates, which are the ones that were the most studied. But I will also refer, especially for ARPES experiments, to this other type of family, which are misfit cobaltates. So these are samples that are grown by the Prismat lab in Caen in France. And they are interesting because you can find exactly the same cobalt oxygen 2 slabs, but they are in a different three-dimensional environment. In between the plane, instead of putting the sodium, you can insert different oxo structure with a different composition. And these structures will also donate electrons to this plane. So that's another way to dope this cobalt oxygen 2 slabs. So typically, you reach range that are equivalent to X 0.7 or 0.9 in this sodium cobaltate. So this part of the phase diagram where you have all these strange correlation effects. And so these compounds are called misfits because periodicity here of the Brouet plane is usually incommensurate with that of the cobalt oxygen plane. And so changing the composition of this Brouet is to change the composition, the doping of this plane. So So it's interesting to compare these two families to understand what is the influence of these layers on the properties of the cobalt oxygen planes. And for ARPES it will also be quite convenient because here you can clean easily the samples between two discrete oxygen planes. So that's a very stable configuration. It's a little bit like the bismuth cuprates. And so this bismuth oxygen plane is protecting a little bit this cobalt oxygen to planes. So that's at the surface it's a much more stable situation than here, where you don't know exactly what happens to the sodium. So it's also one of the motivations is to compare the properties of the two families to rule out maybe some strange effects that could be due to some surface effects. Okay, so I will now discuss a little bit what we see with ARPES. So I don't have much to say with ARPES after the nice lecture by Adam Kaminski. I just recall here that the things we are interested in here are these two basic questions. What orbitals do we have at the Fermi level? And how could we quantify the kind of correlations we have in these phases? So for this study, I will refer for the ARPES work on sodium cobaltates, mainly to the work of the groups of David Hassan and Hondi. And for ARPES on misfit cobaltates, mainly on the work I've been doing with Alessandro Nicolò, who is also here, and who will present a poster on this topic today. Okay, so this is the band structure I've been presenting before and expecting Fermi surface. And so when the group of Hondi first looked at these compounds as a function of x, it's maybe not very clear, but it's x 0.3, 0.5, 0.7. So what they see is a nice hexagonal Fermi surface, like expected here in the calculation. And so you can see that obviously this Fermi surface is shrinking when you add more and more electrons. So that's what you would expect. If you have more electrons in the structure, as it's a whole band, it will get smaller. So this is in a good agreement with band calculation. Now, what they don't see is this small energy pocket near the Fermi level. So there has been a lot of discussion. Could it be because it's a surface effect in the sodium cobaltate, or maybe the sodium is disordered and this will kill these energy pockets? So what we've been observing in these misfit cobaltates is just exactly the same. So a nice hexagonal Fermi surface corresponding to this one and no energy pocket. So it seems for some reason these pockets are really not there here. Another way to try to confirm that is to look at the number of electrons that are contained in this band, just to see if all the electrons that you expect from stoichiometry are there, or maybe some are missing and could be in these energy pockets that are not seen for some reason in the ARPES experiment. So that's what the group of Hondi has been doing. So it's actually very simple in a two-dimensional system, because the number of electrons in this band will just be proportional to the area of the Fermi surface compared to the area of the Brouet zone. It's just because the K vector are quantified in a reciprocal space, and there is a famous theorem by Luttinger saying that this will not change if you add correlation effect. You can renormalize the band as much as you want, but the point where they cross the Fermi level will not change, just to conserve this number of electrons. So here they estimate the number of electrons you have in this band from the stoichiometry, from the measurements, so from the area of the Fermi surface, and here from the stoichiometry, and you see that within error bars you've got quite a correspondence. So it seems that there is no electrons left for these energy pockets, and that they are not present in these systems. Okay, so then there have been a lot of debate on whether correlations could suppress these energy pockets at the Fermi level. So this is a problem that has also been discussed in this school quite often for different cases, and you know that it's a delicate competition, in fact, in between two different effects. On the one hand, you have this on-school scoring that is telling you that it would be better to put electrons in the different orbitals so that they can avoid each other. But if you do that, of course, you lose this crystal field energy. And especially if you have correlation effect and you renormalize the band, so you will decrease the overlap between these two, and this could enhance this crystal field effect. And so at the beginning there was some conflicting theoretical results. Some say, okay, the correlation should increase the size of the pocket. Some say it should should decrease the size of the pockets. And I think it was clarified by this study by Nicky, Barcolet and others, which understood that it all depends on the value of the delta you are starting with. Because you can see, in fact, the two opposite effects depending on this value, that's different delta values. And you can see that for some values, you tend so that the occupation of the orbitals, so you tend to decrease the occupation of these orbitals, so to enlarge the pocket. And for some other value, it will be the opposite. You will completely fill this equality orbital up to 1, and so you don't have pockets anymore at the Fermi level. So we are all back to this problem of knowing what is really the value of delta. And as I've noted, you have in fact quite different values of delta that you can find in the literature. For example, in this paper, they did a chemical quantum cluster calculation, and they find a value of 300 millieV. In the LDA calculation I've been showing before, it's just minus 15 millieV. So you see that there's a wide difference, and as far as I know, it's not really easy to know exactly how to compute it precisely. So it could be that here we just don't have a fancy pocket because this value of delta is a little bit larger than what has been taken in this calculation. Okay, so if the pockets are below the Fermi level, we should also see them in photoemission below the Fermi level. So if we do that, the first thing you notice is that the band that is crossing the Fermi level is actually, so to give you this hexagonal Fermi surface, so this band of A1G symmetry, it's actually a very narrow band. It's just 100 millieV here, and it's exactly similar in the sodium and in the misfit cobaltates. So if you just take this 100 millieV and compare them to the dispersion we were expecting for A1G, it's a huge renormalization effect, just at least a factor 5. So it would really tell you that you have a strong correlation in these systems. Now the situation is a little bit more complicated because you see here that you have all these other bands that you also expect at higher energy. And so sometimes for experimentalists having a multi-orbital system, it's a little bit of a problem because the situation is so much more complicated. And especially you see that you expect an E' G band to cross this A1G band here. So it's reversed here, but so even if you don't see this E' G band here, you could expect that maybe some interaction is giving you a strange structure for this A1G band. So to try to understand this better, what we've been doing with Alessandro is to compare carefully what is happening in two different directions over the reciprocal space, gamma K and gamma M, where you expect a very different interaction between A1G and E'. So it's just turned out that around gamma K, the interaction is forbidden by symmetry, so you see that the bands are crossing without opening a gap. And on the contrary, on gamma M, you have a large hybridization gap between A1G that is breaking the dispersion. So even if you can have some deviation from this picture from the real systems, we do expect to see something quite different between these two directions if this structure is due to hybridization effect. And what we have found is that the structure is indeed very similar in the two cases. So the small band that you see here that's the band that I've been zooming before, so that's the A1G band. And then you see a broad feature at higher energy, which is dispersing towards -1 eV in the two directions very similarly. So we've tried to extract dispersion as best as we can. I will discuss that a little bit later. And we found that indeed, if you compare the dispersion in the two cases, they seem to be very similar. The dispersion of this A1G band is almost exactly the same in the two directions. And for the hump, which is a little bit more difficult anyway to extract precisely, it's also very similar.
Excuse me,
yeah.
What's the color scale here? Blue compared to white?
So blue is small, so 0,
yeah.
right? And then then you have so the maximum is here.
And white is also a little maximum?
No, the white is in between this one. I'm sorry, I should have taken that. Okay, so we decided that this structure is not due to interaction with E', but it's really intrinsic. And we've tried to clarify this a little bit further. We've tried to use the polarization dependence that you expect in the ARPES spectra to separate these different orbitals. So that's something that has been shown by Adam Kaminski in the Nick diets. If you put the polarization in plane or out of plane, you can select orbital of one symmetry or so even compared to this plane or odd compared to this plane, and this is a way to suppress some bands that can a little bit clarify what we can see. So for example here, we expect these two orbitals to be even and this one to be odd. What I've been showing before is even configuration here. And so if you go to the odd configuration, well, you should observe just this black line. What we see is just a broad peak with not much structure, not much dispersing. And so we concluded that Img is quite flat. And this could be consistent with the idea that, okay, Img is a little bit below the Fermi level, so we don't have much of a structure anymore in its dispersion. So if the same is true for the other Img, this gives us a nice way to obtain just Img by subtracting the two different polarizations. So in this way, in this subtraction, you get rid both of the Img and all background effects that you could have in this spectrum. And so we obtain here a structure for the two directions that is representing this A1G line shape, and you see that it has a very well-defined structure with a peak, a dip, and a hub. So this kind of structures, that's something that you can expect if you put interaction in a system. So I just recall that briefly using a cartoon that is in the review of Andrea Damashili. So basically, if you start in a system without interaction, you would just expect to see a Dirac peak that is following the dispersion that you can obtain in a band structure, including no correlation effects. Then, with some interactions, you will have many different effects appearing. So you will renormalize this band dispersion. You will broaden the peak, that will be the lifetime of the quasi-particle that you could measure with ARPES in favorable cases. And you will also reduce the weight of this peak to this value z, and the rest of the weight is transferred to some incongruent structure that could have many different shapes that could form this type of satellite structure that you see here. So here it's a very general picture, and it makes no assumption about the nature of this incongruent feature. So it could be a rubber band in a correlated case. It could also be if you have a strong coupling to some collective excitations. It could be the envelope of excitations of electrons with 1, 2, 3, 4 of these collective excitations. So it's really a many-body structure. Okay, so this structure resembles what we see here. So doing this type of separation, we can follow this structure at different k points. You see that the quasi-particle peak here is the broadening when you go away from the kf. In losing weight, and then this other structure is remained there and is dispersing. And it's something that is very similar to the case of other correlated systems. For example, in mandonites, we have quite a similar structures with a very narrow peak, very small peak near the Fermi level, which form a very narrow band, and a broad peak that is dispersing much faster. So it may also have some analogies with some waterfall structures that have been discussed in the cuprates, where you can see a narrow band at Fermi level and some other structure at higher energies. Okay, so we've been trying different approaches to try to analyze this line shape. And finally, we find that something that is quite direct is to try just to compare the weight of this incongruent structure with that of the quasi-particle peak. If you do that, you obtain a small quasi-particle weight of just 0.50. And what is nice is that if you renormalize this bandwidth that you expect in the LDA by this value of z, well, you obtain something like 0.50, so just the quasi-particle band that is observed in photo emission. So at least it's a self-consistent way to interpret this spectrum, and it goes with the idea that you do have a very small quasi-particle unity scale in this system. Okay, so now there are other signs of correlation effect. For example, this quasi-particle peak is very temperature dependent. It broadens and you lose it when you go to a higher temperature. That's typical of low coherence temperature for these metals. You can see the same peak being at the Fermi level. And what is interesting is now if you try to follow this peak in different compounds which corresponds to a different value of x. Here we increase x from 0.7 to 0.85. you see that progressively you completely lose this peak. Just as if correlation were increasing when you go to higher and higher x. And so this is a little bit the same trend than what has been observed, for example, in this increase of the effective mass in the sodium cobaltates above 0.7. And it asks you again what type of correlations do we have in this limit. Okay, so that's what I will try to discuss now with these two different possibilities. This spin orbital polarons proposed by Calvin, or the influence of the charge order that exists in these spaces. So this idea of spin orbital polarons is basically this one. So you consider here a case where you have a few holes on the triangular lattice, so there will be cobalt 4 plus here, and you can imagine that this hole will distort its surrounding. So on the neighboring cobalt 3 plus side, you could have a distortion that will be able to left the degeneracy between these EG orbitals and maybe allow some excitation of one electrons to these EG states. So then these cobalt 3 plus that are near the cobalt 4 plus can become magnetic with S equal to 1, and that of course a very different object that you have here coupling all these different degrees of freedom.
Is that general picture consistent with the NMR?
No, fine. So it's not easy to answer. So I mean, the one problem with this picture is there has never been some direct observation of magnetic cobalt 3 plus. Now it's, I mean, this picture is very naive. That is telling you that this will really be stabilized at a static level. So it could be also some excitation. So in fact, what they discussed in this paper is that in fact, when you have a cobalt 4 plus that will go from one side to the other, you will create these states as some vertical excitations. And so in this case, it's not really easy to know what you would observe on the NMR time scale.
Such thing has been seen by neutrons for perovskite cobaltates, slightly above perovskite. Nothing over to 3 very slightly above bipoles.
Yeah, but so there are other types of cobaltates where you have, well, it's known that you can have these high to spin states.
Cobalt 4 plus, which creates rather big magnetic polarons, 6 or 7, around the cobalt 3 plus becomes magnetic, and forming total polaron. That's Andrei объясняет.
Yeah, so in this family, in the bismuth cobaltate, for example, it's known that at high temperature, about 300 K, you can have, you can see in the susceptibility some accident. It can be also explained by the transition of cobalt 3 plus from low spin to high spin. So these states are not very far in energies, but it's still a question whether they can really be important for these states or not. So what I find nice in this picture is that it really explains quite directly that you would find this type of correlations just at the high X limit. Because if you are in a situation like that where you have few cobalt 4 plus, you see that they will be far apart spatially, so they don't interact, and you can really stabilize this type of effects. If you start to have more and more holes, so you will have a dense lattice of that, and at some point they will start to overlap, and of course this will weaken and destroy this type of effect. So it's a way to really explain that you should get this physics in this limit where we observe this type of correlations.
For point 9, stability is Curie-Weiss, yeah?
Yeah.
Is it possible to estimate what's effective moment per one hole?
So, I mean, that's what that's what Kalulin was doing actually in the first paper, so I think it's this one. So, I mean, the main point was that this type of effects were able to explain the Curie-Weiss susceptibility.
I mean, just experimentally simply fitting by Curie-Weiss, and from nominator you know what's effective moment per one.
Yeah, but it depends. When you try to do this fitting, it's always a little bit difficult because so the moment you get depends very much on the Curie-Weiss temperature you get. So I mean it's consistent, but it's not completely straightforward to interpret. It depends a little bit on what you choose as Curie-Weiss temperature.
Takura, they made similar measurements for perovskite material like the dot, and then they found that per hole effective moment is something like 10 to 15 Bohr magnetons per one hole. That's the deep means that they create big slot. So I just wonder whether similar treatment has been done here, right here. Be careful thinking of sensitivity, that's really.
So I don't know exactly the answer. What I know is that when you try to fit, you have this problem of choosing the pure device compared to the norm. But, okay, so now in this paper, for example, so they compare this model to our ARPES data, and they find actually quite a good agreement, even with this value of z that is that can be very small. Okay, so now if we try to look the problem a different way by starting from this charge order states that we have. So as I said, it seems that this charge order is correlated in this case to the position of the sodium, and it was actually proposed quite early by the group of Gautier that sodium could indeed induce correlations in this limit, because the sodium could bond with one electron, and for a very narrow impurity-like band where the correlations could be very important. And so one thing you could say is that if this is all due to sodium, well, we have a very easy way to check that by looking at the misfit cobaltates where we don't have sodium. And in fact, at the beginning, it was really our motivation to start to study this type of materials. But then we realized, looking at the structure more closely, that here we also have these A atoms that are barium 2+, strontium 2+, or calcium 2+, that are pointing towards these cobalt-oxygen planes. So here you also have a situation where all cobalts can see a little bit of different environment. And in fact, the positions are exactly similar to what you've got in the sodium cobaltates. So if you have this triangular array of cobalt here, some cobalt will sit directly below or above barium atom, and some cobalt will be in the triangular array of atoms. So this could create a difference between the different sides that will also modulate the charges in these planes. So we don't have direct evidence that this is indeed happening in these planes. What we see is that there is some influence of the Russell periodicity on the structure of the cobalt-oxygen 2 plane. So for example, if you do a long scan across different Brouet zones, so two different Brouet zones here, you see these 4 bands that are giving you these 2 hexagonal Fermi surface. But you can also see that you have some additional bands, and if you map their weight, they create this hexagon that is just shifted away from the gamma point by the periodicity that is related to the periodicity of the Russell. So it tells you that there is some reconstruction of the electronic structure of the cobalt-oxygen 2 plane with this periodicity. Of course, it doesn't tell you if it goes as far as localizing charges with this new periodicity. One thing we can do to try to have some information about that is to look again at this Luttinger theorem. So before I just presented this part of the curve up to 0.7, where it follows very nicely what you would expect for the Luttinger theorem. What has been shown is that if you go to higher values of x, then suddenly it seems that you have a deviation from this theorem. And so once again, if you observe it in the sodium, you could wonder whether maybe the stoichiometry at the surface is not the same as in the bulk and so on. So what we've been trying to do is to compare what we could have in a misfit, and we were surprised to see that comparing these 2 compounds which have different doping, we obtain these blue points here for 0.7 and this green point for 0.75. So it seems that we have also a deviation that could be consistent with the one that you observe in the sodium cobaltates. So what could it mean if you take this deviation seriously? What it's telling you is that you have more holes in this Fermi surface than what you expect. And that's exactly what you would expect if you have some electrons that are trapped on some of the cobalt sites. So maybe this deviation could be just interpreted as an evidence for the presence of cobalt 3+ sites in these systems. That would be present both in the sodium and in the misfit cobaltates. Then you could wonder whether it's an intrinsic tendency of the cobalt-oxygen 2 planes. And maybe to understand this tendency, you could understand it by using the non-local part of the Coulomb interaction. So I'm showing here a phase diagram taking into account both on-site correlation and inter-site correlation. So it was not drawn for the case of cobaltates, it's for the case of low density electron gas, but it just gives you the idea that even if you have rather small values of U over W, if you increase this inter-site correlation effect, you expect to go to some other states that will first be metallic. So it may be what we witnessed in this case, and indeed very recently, Lecherman has done some calculation starting from this Kagome structure and increasing the value of V. And he's finding here that indeed the Z value is found in this different stoichiometry is very dependent on this value of V and can be significantly lower in this case. Okay, so that's basically what I wanted to say, and to conclude briefly, I think what we know for sure here is that we have a very small quasi-particle energy scale, and we have a high sensitivity to external perturbation like sodium or rock salt potentials. Now, what is a little bit more difficult to know is what is the driving force and what is the consequence of the other. So we could, of course, if we have this small quasi-particle energy scale to start with, it's quite logic that they will be very sensitive to any perturbation because they will be easy to trap. Then maybe we should start from this kind of potential that is creating also some kind of disorder for electrons in the cobalt oxygen to play, and that maybe it's creating this small quasi-particle energy scale. But I think in any case, this creates this rich phase diagram with original properties that are interesting for fundamental reasons and also for applications. Okay, so finally, I want to mention all the people who have been involved in this work. So the work I've been doing at some different synchrotrons in Swiss, Italy, and in France at Soleil. And samples were borne by the Chris Martin camp and actually by CBA there. So thank you for your attention.
Questions, comments?
Concerning this discussion about the crystal field splittings, are there any infrared experiments or would infrared experiments here help maybe to give some idea about these values if the transitions are of course not forbidden?
I think the problem is that two bands overlap very strongly. So this crystal field effect
Very small.
Yeah, it's very small. So the bands for sure do overlap. So I don't think they will be able to distinguish from an excitation between the two bands because they are completely mixed.
And actually this conclusion about the principle of Mariana here I'm saying is that the LDA doesn't give you the right value for the crystal field. But isn't that conclusion based on a calculation which precisely neglects the intersite interaction? So that could also change, maybe?
I don't think they do a calculation on delta. They just highlight the fact that the difference between, for example, the different theoretical approach is really due to the value of delta.
Right, but if you were including the intersite interaction in your calculation, is it clear that with the LDA delta, you don't get the right result?
No, it's not.
Yeah. So if V is important, some of the questions are in there.
These are very high thermal power effects. Is that across the planes or in the plane?
I suppose it's in the plane, but I'm not aware of measurements that would have tried. I don't know if it's even possible to measure.
I was kind of wondering, same thing goes for the superconductivity. Is there any anisotropy in there?
I don't know about that. I would guess it's going to physics in plane. I mean, they are very two-dimensional methods in this house.
Yeah, well, I would, for the thermal power, would guess it's the other way around. Because I guess you would have.
I mean, for example, one thing that is also interesting in comparing the sodium and the misfit cobaltates is that you see that the planes are much further apart than the misfit cobaltates. And the misfit cobaltates also have a very high thermoelectric power, even higher in some temperature range than the sodium cobaltates. So I would not imagine that talking between the different planes is important for thermoelectric power. But I don't know much about thermoelectric power, to be honest.
For superconductivity, precisely you are putting water which creates a distance between the sodium plates. So the carbon oxide plates. So the system becomes very
So the idea of putting water, I mean, of course it puts the planes further apart, but it could also, the idea is it could also screen the potential of the sodium, and maybe that's why you get a better method that can go conducting.
Other questions? Everybody getting hungry? Or you want to comment on the difference of the yellow and the brown?
It's just that in the crystal structures, the two sides are different. We use colors which are different because in the crystal structure they are slightly different. But for the physical properties, we find the NMR shift, the T1 are the same for the yellow and the brown, or the blue, the dark blue and light blue. So for the sake of being clear, we show exactly the situation on the crystallographic side, but on the magnetic properties we have only two sides, the clear and the blue.
Wasn't there a big view of water, since some view that water was responsible for radiation from the PP hierarchy? You had water insertions and
Can you repeat the question?
The water will screen the potential of the sodium.
Can you repeat the question?
Can you repeat the question? They directly didn't hear. Or
The question is the role of the water for the superconductivity.
yeah, the whole of water was a
Okay. And the answer?
So yeah, the answer is that so two things that you do with when you insert water is to put the planes further apart. But one thing that seems to be important is that water will screen the influence of the sodium potential on the cobalt oxygen planes, and so maybe introduce these other effects that could just reduce superconductivity in this case. As far as I know, it's the best way to understand why you find superconductivity actually only in this water phase.
This is the point for which we had an argument from NMR, which was that in the 0.3 concentration regime, the sodium was dissolved. It didn't order as it does when you go to higher concentration. And we noticed that when you put water, you do not change at all the properties of the normal state. So the normal state properties are independent of whether it's dry or wet. But superconductivity only occurs in the wet part, in which situation, in principle, the disorder is clean.
And there's no other easy way to screen it by substitution.
So far, nobody has done that.
Has anybody tried wine?
Japanese did.
Only for the
By
nickel.
the way.
Only for the nectar.
Yes,
Not for the cobalt.
on pnictides. On pnictides, Japanese did.
Not for the cobalt.
Wine is the best, right?
Red wine.
Bordeaux, Bordeaux, they said, for the pnictides.
No, actually, Patrimonio is much better. They just haven't had access to it.
Okay, if there are no further urgent questions, then we could check if Henri has a sample or Veronique has a sample, we go for lunch and we do the experiment. Let's thank Veronique again.
I told you I have a theory.
You have a theory for the wine?
Yeah. Because this was the sulfur compound. So they used the wine with sulfides. If they used the wine without sulfides, yeah, exactly. They actually were doping unintentionally.
All of you